All right, so for this lesson in Chemistry 30, we're going to talk about equilibrium concentrations again. This section is called ICE charts. This is what I have called this, ICE charts. Now, I'll show you, down here I show you what ICE represents, okay? It's an acronym for other words. But let me just set up the problem here, okay? When we've talked about Le Chatelier's principle, we're talking about systems that are already at equilibrium, right? So you've got A, B, C, and D, and they're at equilibrium already. The questions that this method is going to help us understand is before equilibrium is reached, okay? So when you start off with just two reactants, let's say, just reactants, those reactants are going to be allowed to react and then reach an equilibrium. So if you're asked a question about, here's some reactants, we're going to allow them to react until they get to equilibrium, then what are all the concentrations of everything that's there? That's a totally different question than you're at equilibrium and let's change some conditions, okay? So let's just read through the notes here. When we're given reactants only, okay, so this is what the situation is here. We're given reactants only, or in some cases we're given some reactants and some products, but they're not at equilibrium yet. Then what we're going to be able to do with this method is calculate future equilibrium concentrations of all the substances involved in the reversible reaction. Okay? So what I'm going to do is I'm just going to zoom in here a little bit because this is kind of small and I want to just show this in a bit of a, there we go, a bit more of a full screen. Okay. So what we're talking about here is we're just given some concentration of A and some concentration of B. And we're just putting them in a container, let's say, and we're just allowing them to react. Okay? As they react, they're going to produce C and D. Okay? And notice this arrow. It is a forward reaction. So A and B are busy reacting, producing C and D. Now, at some point, there's going to be a lot of C and D in the reaction, and the reverse reaction is going to start happening, right? It's like, okay, A and B, you've done enough reacting. Now there's so much C and D that they can't help but react and push it the other way. Okay, so obviously we're dealing with a reversible reaction. And so we have these three stages, okay? You get that, right? Everybody gets that? So think about it this way. Here's a totally just random, another example, not chemistry related. Let's say we're at you're at a wedding or something, and there's a dance, okay? And you're having a dance, and you know, we have the guys over here and the girls over here. The music starts. Well, what happens is the guys and the girls, you know, whatever, start pairing off, and they go on the dance floor, and they're dancing, and this is happening one after the other. Okay, A and B are reacting to produce, you know, different dancing couples over here on the dance floor. Okay, so this is just going to happen. People are going to start dancing, and you know, they're going to start pairing off and going on the dance floor. That is step 2. Okay, so we have guys, we have girls that are going to dance, and they pair off, and now we have dancing pairs over here. Well, at some point, these dancing pairs are going to get tired or whatever, and what's going to happen? They're going to say, okay, I'm done for now. And then they're going to go back to being non-dancing people, right? And so then if you think about this through, let's say we come to this situation where we have people pairing off to go dance, and dancers saying, I've had enough, and now they're going to come back and just go sit down and relax. If this happens at the same rate, we are at what? Equilibrium. Okay, that's an equilibrium situation. Okay? Now the question that we're going to be able to figure out is, just given this group of guys and this group of girls that are going to dance, okay, if you allow them to react, knowing that, now there's some things we need to know, okay, and I'll tell you about those a little bit later, but we're going to be able to find out at equilibrium, all right, how many dancing couples are we going to have and how many separate people sitting off on the side are we going to have? You're going to know that, and you're going to be able to calculate that. All right? So now let's bring it back to the chemistry example. Okay? How do we know how far this goes right here? So if it's a reversible reaction, at equilibrium, the question is, are we going to end up with a lot of C and D and just a little bit of A and B at equilibrium? Or is it going to be the opposite way around? Is A and B going to react just a little bit and then C and D are going to right away shift, left and start reacting? Well, in this case right here, I don't know if you guys have noticed this, but I actually drew kind of little rectangles over here and larger rectangles on the right side. This represents a situation where most of the reactants have reacted to form products. And at equilibrium, we have a little bit more product than reactant. Now, if you notice down here, you see this? I said the KEQ in this situation was around 20. And that, of course, is larger than 1. And so we would guess that there would be more products present at equilibrium. Okay? Now, if this KEQ was 200, how would this equilibrium picture look? Anyone? If this was 200, how would this equilibrium picture look? Huge C and D, right? Huge C and Ds. Very good. Big, huge C and D. Let's show that, okay? 200. Here we go. Big, huge C's and D's right there. And what would it look like over here? Big A and B's as well? Just little. Just teeny. I can't even draw them that small. So yes, if this was 200, that's what we would expect. Now, guess what? Here's the thing. If you know the initial concentrations and you know what the KEQ expression should look like, and you know the KEQ value itself, you're going to be able to calculate the concentrations of all the substances at equilibrium. And that's what we're going to do. And we're going to use the ICE chart method. Okay? So now let's zoom back out here. Get to 100%. Okay, 100%. Zoom back out. Now, where do I get ICE from? Okay, here it is. Here's where I get ICE from. I is the initial concentration of everything that you're given at first, and usually it's the two reactants. Okay? Sometimes it's, hey, we've got initial concentrations of reactants and products, and they're going to react. Now you find out, but that's later. Okay? Initial concentrations, that's what I stands for. And remember, please, always in moles per liter. Okay? Capital M, molar. Not grams per liter, and not just moles either. It's got to be concentration. So moles per liter. Okay? Amount per volume. Concentration. C is the change in concentration. So this is where it gets a little bit tricky, I would say. This one's really easy. C, some people get kind of tripped up at C. It's not that hard once you get some practice with it. But the second step is the change in concentration. So, for example, we know that A and B are going to decrease in concentration, right? We know that C and D will increase a little bit. That's what's going to happen. But how much? Well, I'll show you how we know how much. And then E is equilibrium. So it's equilibrium, and what do I mean at equilibrium? It's the representation, and of course we're going to have some unknown variables here, so there's going to be a little bit of math involved. Representation of, or the expressions of, concentration. Okay, of each substance at equilibrium. Alright, so that's where we're at, and I'm going to do an example here with you. Okay, so I'll leave that ice up there, and let's work on this example. So this is what you're going to see. 1 mole of H2 and 1 mole of I2 are placed in a 0.5 liter container. So we have 2 reactants initially that are placed in a container. And they are going to be allowed to react at a certain temperature. Remember, The KEQ is temperature dependent. We do not have to include the temperature in any of our calculations, so don't worry about that. The 448 you will never see again, but what you have to know is that the KEQ is always linked to a temperature. So if this was at a different temperature, the KEQ you would get would be different. Okay? So the KEQ is 50. What are the concentrations of all substances at equilibrium? Okay? Concentrations of all substances at equilibrium. If you're given a question like this, you're immediately going to say, ICE chart. Awesome. Well, let me show you how that's going to work here. Now, different people have different ways of doing this. I'm sure this is the way I do it, the way I teach it. So, the examples, all the problems that I'm going to be doing here, I'm going to be doing it the same way. All right. If you figure out some other way from the internet or whatever, from some, older brother or your dad or mom or whatever, that's fine. Doesn't matter to me. If you mess up with your way, don't come crying to me though. Okay. If you don't understand your own way, do not come crying to me about it. Because I'm going to show you the way that I've been doing this for now how many years? 20 years. This is the way that I like doing it. This is the way that I used to do it all the way through. So, I don't know why I said that just now, but I'm just saying. Okay? Every teacher goes through that, right? I showed you how to do it this one way. But I like this way better. Okay, fine, but it doesn't work. Okay, well, maybe you should try my way, but I don't like your way. Okay, so I'm just going to keep going here, okay? So, what you're going to want to do is, first of all, before you fill out the chart, you're going to want to write a balanced chemical equation, okay? Now, I do have over here some steps that I have written out, and I'm going to allow you to do this now because I think that this is important. So on the side, maybe on the side, leave some room to do this. On the side of your notes, on the side of your page, or leave some space and do it underneath. We got to get going. All right, we're going to run out of time here. All right, make sure that all amounts are in concentration. So we need concentrations. That's first big step, concentrations. Number 1, moles per liter. I'm going to be flipping back and forth, sorry. But look at this. We have 1 mole and 1 mole. That's not a concentration. You have to include the 0.5 liters. So that's going to be what? 1 mole divided by 0.5. What's that? 2 molar. Okay? You have to know that. You have to write it in okay. Okay. So okay. Concentrations. All right. I think at this point, actually I didn't know this wasn't in here. We're going to do 1B, balanced equation. I think this is already assumed for most that you have a balanced equation, but you may not. So make sure you have a balanced equation. That is 1B. Okay? We have to deal with concentrations, but you also have to have a balanced equation. So, 1B, balanced equation. We have H2 plus I2 produces what? HI. Is that balanced? No, you need a 2. Good. So a 1 goes there, a 1 goes there, and a 2 goes here. Awesome. Balanced equation. A lot of times you'll be given it, but if you're not given it, you have to create one. All right. Step 2 says create a 3-row ice chart. All right, here we go. 3-row ice chart. Create an ice chart. Number 2. If you want to write that down. I.C.E. Okay? Make a 3-row ice chart. 3 rows. 1 on top, that's awesome. Okay? And what we want to do here is we want to make columns that the same number of columns as we have number of gas substances. So these are all gases, so we would include them. And this is what I like doing. Again, I like putting on these columns 1 H2 up there, 1 I2 up there, 2 HI up there. All right? All right, so initial concentrations, we said 2 molar, right? Okay, we're going to fill out the first part of this. 2 molar. Here, 2 molar, right? 1 mole of each in a 0.5 liter container. Now, how much HI do we have initially? Initially, none. So it's going to be a 0 there. Okay? All right, so this is going to be, I'm going to finish this ice chart in the next video, and we'll finish the steps next class. All right? So look for video number 2, ice chart number 2.